Hello, this is Sadbir. In this video tutorial, I will give you the introduction to real analysis. What is a real analysis? As you can see, the real analysis is a word made up of two words, real and analysis. Here, the word real refers to real number, real sequence, real series, and real function. And analysis refer to study. So in this course, we will study the real number, real sequence, real series, and real function. Real analysis is the foundation of our calculus class because in our calculus class, we study all the functions which were defined on real numbers. So let's first begin by studying the number systems, what number systems we had and how these number systems were introduced in ancient time. Our first number system is natural number system. It is denoted by capital N, and in natural number systems, we have number 1, 2, 3, 4, and so on. These natural number are also known as counting number because in the ancient mathematics, they are used to count the object. So for example, if we have to count certain number of objects, we use 1, 2, 3, 4, and so on. So this is the reason these number are also known as counting numbers. What is a whole number system? In a whole number system, you add one more number, which is a 0, and then you have all the natural number also. And 0 is a denote of nothings in the mathematics. So for examples, if you have 3 apple and if you give these 3 apple to somebody, how many apple left with you? The answer to that is a nothing, and that nothing in mathematics we denote by 0. So 0 is also a very important number, and it is the part of whole number system. So as far as the mathematical operation on natural number, we can do two type of math operation. We can add the two natural number, and if we add two natural number, we get another natural number. For example, if you have one object and then you have two object of a certain kind, and if you combine, then you have a total number of object, which is 3. You can also multiply the two natural number, and then you get another natural number. So these two math operation can be these two math operation can be applied on natural number system. The same thing was true for the whole number because it has only one extra number in it. So nothing basically changed as far as the concern of mathematics. But there was a one issue in this number system that when in term of the financing or trading, if you own somebody, that cannot be basically denoted with that number system. So for examples, if I own somebody $7 and then in mathematics, we were not sure that how to denote, like if we denote it by a counting number 7, so 7 was not sure it is a referring you own somebody $7 or somebody own you $7. So that was an issue um, in counting or in financing with these number systems. So then the mathematician introduced a new number system, which is they called integer. And in integer now we include the negative numbers, which has 0 and all the natural number of counting. So this number system is used basically again for counting, but now we include basically the counting of negative objects. And in this number system, you have the addition operation. You can add two integer, and then you get another integer. And now you can subtract also. And you can subtract one integer from another integer, and then you get another integer. And the multiplication operation was also there. So you can multiply two integer and then you get another integer. So in this number systems, we have three operation, addition operation, subtraction operation, and also the multiplication operation. Now, one of the most important number system is the rational. Now we will discuss one of the most important number system, which is the rational number system. And it was introduced to solve the problems when we are imagining the object. Let's suppose we have a rope of length 1, and if you want to divide these rope into 3 pieces, and how much each person will get that piece of the rope. So that cannot be counted by using the integer, whole, or natural number system. So then we introduce the rational numbers. So what is a rational number? So they are denoted by the letter Q. They are of the form P and Q. They are all written in fraction P and Q form, where P and Q both are integer. And here we do not need the Q is equal to 0, because mostly this number system is used for dividing object into certain number of people. So we don't want to divide something into 0 number of people. So 0 was not included in the denominator in that number system. So this number system was really helpful when you need to measure the certain object or the length of the certain object. So we introduced this rational number system. So now, so for the rational number system is the largest number system, because rational number system include integer, whole, and all natural number system. And do we need any other number system which is bigger than that, or or this rational number system is enough to do all the problem which is related with the finance or business? So this is my next question, is that can we measure the length of any segment with this rational number system? Because if it is so that we can do all the engineering problem just on a rational number system, we do not need another number system. Unfortunately, the question to that answer is no, and we will prove that why you cannot do it. So here, let's suppose the length of this segment is 1 and the length of this segment is 1. Then can you measure the length of this segment? Let's suppose this is A, B, and C. Then the length of BC, is that a rational number? This is the question. Can you represent the length of this segment BC by a rational number? The answer to this question is no. Let's suppose this length of this BC is X. So then by Pythagoras theorem, the hypotenuse square is equal to the square of the base and opposite. This is a 1 square plus 1 square on X square is equal to 2. So we will prove that X cannot be a rational number. So here, this is our theorem. In this theorem, we will prove there is a no rational number whose square is 2. Or in other words, there is no rational number which satisfies this equation. So if we prove this, then it means we prove that this segment, which is a BC, this segment cannot be represented by a rational number. So you cannot write this length as a P and Q form. So let's begin this proof. We will prove this theorem by using the method of contradiction. This is our first theorem of this course. We will have many other proof, but this time I will use this method. This is the method of contradiction. In the method of contradiction, so first I will basically take the statement and assume that the opposite to that statement. For example, what I need to prove in this theorem, we need to prove X is rational. We need to prove that the length of the segment BC is rational. By contradiction, in this contradiction method, what I will assume, we will assume x is not rational. For example, sorry, I need to prove that x is not rational. So the length of the segment cannot be basically measured by a rational number. I will assume the opposite to this statement. So what I will assume is we will assume x is rational. So I assume that x is irrational. So what I will do is I will prove some contradiction that this statement should not be true and cannot be true. So now if x is irrational, we know that all rational number can be written as p and q form, where p and q both are integer and q cannot be equal to 0. So this is the definition of rational number. So I just write it down. And then I will also assume, we may assume P and Q have no common factor. Because if P and Q have any common factor, I will cancel it out and consider the lowest term of P and Q. So this is without any loss of a generality, I can assume that P and Q have no common factor. Now we will begin and we will basically prove that this statement cannot be true, which I assume. So in order to do that, I will take that x and plug into this equation. So this gives me basically p square divided by q square is equal to 2. And if I multiply q square on both sides, I will get p square is equal to 2 times q square. And this statement says that the p square is the multiple of 2 and some integer q. Because if q is an integer, the q square is also an integer. So this integer is multiplied by 2 is equal to p square. So that implies p square is even number. Even number. Because any multiple of 2 is an even number. So this p square is a multiple of 2. So p is an even number. So what is a p square? It means a p is a product of p and p, which is a even. So the product of p and p is a even, and we know one property. If we have two even number, if we multiply the two even number, we get even. And also if we have two odd number and we multiply them together, we get odd. The product of odd number is odd. The product of even number is even. So this will give me P is even because this can only satisfy the first property. So P is even. So if P is even, we know that any even number can be written as, so if P is even, it can be written as multiple of 2. All the even numbers are multiple of 2. So I can write P is equal to 2 times R, where R is some integer. And now if I plug that P is equal to here, then I will get 2R, the square of that is equal to 2Q square. And if I simplify this one, I'm gonna get 4R square is equal to 2Q square. And if I further simplify that, this is again 2 divide over, and this is going to be a q square is equal to 2r square. And this simply tell us q is a multiple of 2, or in other word, q square is even. And using the same argument, I can prove that Q is even. So in this proof, what we prove so far is P and Q are both even. So we prove uh, P and Q both are even. If Q and P both are even, it means P and Q have common factor of 2. Because all even number has common factor 2. So it means P and Q both have a common factor 2. But you can see this is a contradiction because we assume that P and both Q do not have any common factor. Or even if have a common factor, we will cancel it out. So, but here we prove that P and Q has a common factor, which is a 2. So it means this is a contradiction. So this is a contradiction. So if this is a contradiction, it means this statement is not true, or in other words, the opposite to that statement is true. So this implies X is not rational. So it means the rational number system is not complete because we found a number which is not rational. Or in other words, if you have two numbers which are rational and you want to compute the length of that segment, which is basically the made of the Pythagoras theorem, the right angle triangle, the third side is not a rational number. So in other words, it is the proof, the theorem one implies that there is a hole in the rational number system. And also you can see that if you draw the number system, let's suppose you have 0 here, you have 1 here and 2 here. And here is somewhere 3 half, which is a 1.5. And the proximate, if you approximate this length by a rational number, the approximate this length is going to be somewhere 1.4, which is a very close to this number 1 half and here. And that number, which is basically x square is equal to 2, or another word you can say x is equal to the square root of 2. That number square root of 2 is a hole in the rational number system. So between the two rational number, there is a number which is not a rational. Or in fact, this is not the only whole. There are many other whole in the rational number system. For example, square root of 3, square root of 5, even pi, which is a somewhere here, 3.14 after 3, and e, which is somewhere here, 2.7. So there are so many whole in the rational number system, and these whole are filled by irrational number. So we do not have a proper definition for irrational number, but we will call all the number which are not rational, numbers which are not rational. We will call that number irrational. Or in other word, if we find a number which is not rational, we call that number irrational. And for example, we find that a square root of 2 was not a rational number, so this is an irrational number. Similarly, you can prove square root of 3 is not a rational number, and therefore it's an irrational number. Similarly, pi, which is maybe a difficult to prove, but this is also not a rational number. And similarly, this number e is not a rational number. So these are all irrational numbers. Now, finally, what is a real number? The real number system is denoted by a capital R, and it is the union of the rational, and then we combine with all the new irrational numbers, which we will basically find with those numbers which are not rational. So this is our number system. So we will also basically prove at some point that this number system is complete. Basically, all the mathematical operations which we need can be done by using this real number system. And also we have studied that all the theory of the calculus was basically based on this number system, which is a real number system. So this is the largest real number systems we have. In future, if you find a number which is not a rational and which is not a irrational, or another word which is not a real, that will be another branch of mathematics which introduce a new number system. But so far we have the largest number system is the real number system. Now I have a few practice problems for you to practice. My first quiz problem is here. Please pause the video for 1 and 2 minutes and work on this problem. Here is the second quiz problem. Again, please pause the video for 1 and 2 minutes and work on this problem. Also, this is the end of this video. Thank you very much for watching. I will see you in the next video. Bye for now.